So our first speaker today will be Federico Carta, who will tell us about flat vacua and divisor topologies. Please.
Okay, thank you very much. As a first thing, I would like to thank the organizers for allowing me to be here. It's always very nice for me to speak to this amazing Stringfino audience. I will talk about flux vacua and divisor topologies. And my talk is based on these three recent papers that appeared in the last couple of months with two amazing collaborators, Alessandro Minino and Pramod Shukla. Big part of this talk is based on a paper that I recognized very nice and also important one by the group in Cornell, which is vacua with small flux superpotential. So let me start with some introduction. One of the main goals in string phenomenology is to make concrete models, which should do for us two things. They should reproduce the established low energy physics, like standard model or lambda CDM at low energies, and they should also extend the established low energy physics by providing new candidates for example, dark matter, inflation, and so on. A usual setup for model building is type 2B string theory compactified on a compact Calabi-Yau threefold. However, in this case, the 4D effective field theory would be with 8 supercharges for the n equal to 2 Sugra. So more realistic scenario is done when we consider n equal to 1 effective field theory arising from modeling by an orientifold action, which is composed by some holomorphic involution on the Calabi-Yau plus some worksheet parity on the left movers. Now we consider this Calabi-Yau orientifolds, and in particular we choose orientifolds with fixed loci at codimension 1 and 3, namely O3 and O7 planes. So this is a typical setup for flux landscape as explained in seminal papers in GKP, in KKLT, and so on. Now, crucially, properties of the Calabi-Yau orientifold will fix properties of the low energy 4D effective field theory. In particular, the number of fields and the type of fields that we have in the 4D theory will depend on topological properties of the Calabi-Yau. The orientifold will split cohomologies into even and odd sector, and in particular, the dimension of even and odd subspaces will count the number of fields that we have in the 4D theory. We have H21 minus complex structure moduli UI, which will be the main protagonist of this talk. We also have H11 minus 2 form axion, H21 plus vector multiplets of U1, and also H11 plus Kähler moduli. As I said before, we mainly focus on complex structure. So let me briefly recall how complex structure moduli stabilization work. We work in the supergravity limit at large complex structure. So we have a prepotential that depends on the complex structure moduli. And it's composed of two parts, a polynomial part and an instanton part. Polynomial part takes this form where the coefficient here are the triple intersection numbers of the mirror Calabi-Yau compared to the one we are compactifying on. This other coefficient also depend on topological properties of the compactification space. I will not enter in details on those. The instanton part will depend on the complex structure exponentially, and the coefficients will be related to some topological invariants of the mirror manifold known as the Gopakumar-Vafa invariants. From prepotential, one can derive a Kähler potential, which depends on the periods of the holomorphic tree form on the Calabi-Yau. And famously, there is also a superpotential, Gopakumar-Vafa-Witten superpotential, depending on complex structure moduli through the tree form, and also the dilaton, the axiodilaton, which I call S in this talk, and importantly, the fluxes. So from the Kähler and superpotential, one can derive a scalar potential, and one can stabilize complex structure moduli. After stabilization of a complex structure moduli, the vacuum expectation value of the Gopakumar-Vafa-Witten superpotential will be what we call W0, which will be at this point a complex number. Suppose we have done so, suppose we have stabilized complex structure moduli, then we still need to stabilize Kähler moduli. The effective field theory below mass scale of complex structure moduli describes H11 plus Kähler moduli with a superpotential that, say we focus on the KKLT setup, takes this form. So here W0 is a classical constant part, as discussed before, and then we have a non-perturbative part involving the Kähler moduli. This part can arise, for example, from D7 brains wrapping some fork cycle and doing Gaugian condensation, or E3 brains wrapping some fork cycle. Anyways, the crucial point is now the following. Every time we have a superpotential of this shape, this type, we typically run in a control problem, which is a Dine-Seiberg type of problem. Essentially, if the coefficient W0 and A are all generic, like order 1 type of numbers, then it will happen that the vacuum solutions for the ADS supersymmetric vacuum that we have will lie inevitably at a small volume. And this is a big problem, because of course, I cannot trust the supergravity in a regime in which my volume, Einstein frame volume of a Fourier cycle, is the same order of magnitude as the length of the string itself. So the value at which we have the ADS KKLT minimum is depending on W0 in this way. So we see that if instead of a generic W0, we have a very, very small W0, then this vacuum will be pushed at a larger real part of T. So in order to have control on this step, we need to have a W0 that is sufficiently small. I would say at least 10 to the minus 4, but even smaller would make us feel happier, having more control. So one can ask a question. One can ask, this exponentially small W0, is it generic in the landscape, or is it fine-tuned? Do I need to work really hard to get it, or I can get it easily? And this question, I think, is very important, because suppose it was not possible to get the small W0 at all, then the SUSY ADS minimum would be very unreliable and questionable, and any successive attempt to do the sitter as well. And of course, the question of having the sitter in string theory or not, it's on the table. It's an important question. It's not understood question, I would say. So understanding the first step of the ADS vacuum is very important. And it's also impractical to look at all the models one by one, because the landscape is huge. So I cannot look at all the models one by one. One needed a solution to this problem, and this solution came in a very nice and important paper by Demirtas et al. In 19. They propose a nice algorithm to construct models that by default have a small W0. The steps of this algorithm are essentially two. First one chooses fluxes wisely to stabilize in a supersymmetric way perturbatively all moduli apart one linear combination. Step 2, the flat valley is then lifted by taking in consideration instanton correction of the tripotential. Let me briefly recall how this works. So to find perturbative supersymmetric solution, we look at the covariant derivative of the superpotential, and one way to set them to 0 is by requesting the superpotential itself to be 0 and the covariant derivatives with respect of moduli to be 0. Superpotential takes this form, the derivatives take this form, and we see that there is a solution of the following form. The UI complex structure will be all proportional to a constant vector m, and the constant of proportionality is the axiodilaton. One can see that if you take this, say, ansatz, and you plug it in these equations, you can get 9, 10, 11 to be all 0, provided that the flux vector m satisfies some choice. I cannot just choose it randomly. So it has to be orthogonal to the vector of the fluxes for H. And it should satisfy this relation with respect of the triple intersection numbers. We should also request that M lies inside the Kähler cone of the mirror Calabi-Yau. And finally, there is a tadpole constraint cancellation for the fluxes F and H. So let me show a very not so well drawn picture to try to explain what is happening. So at this stage, we have in complex structure modular space, we have a valley, and we have a flat direction where U is SM, essentially. So you can think that all moduli are stabilized apart from the axiodilaton at this stage. Then you want to stabilize the axiodilaton by taking in consideration the instanton correction, essentially. The effective flux superpotential will take this form. Here we already substituted U equal SM. And the coefficient ADI will depend on the Gopakumar-Vafa invariance of the mirror manifold. So depending on the numerical value of these numbers, that of course depends model by model, you can have in some case that the choice of flux that you had before plus these values of the Gopakumar-Vafa invariant will be such that you stabilize at a very small W0. Now, this is a review of all the story. What do we do now? We want to look for this vacua systematically in a large scale and make a classification and a scan of them. You can see there was also some related work in this direction. So which class of manifolds we choose to do our scan? We choose to focus on complete intersection Calabi-Yaus. So this is a very famous database of Calabi-Yaus defined as zero locus set, the zero locus X of a set of homogeneous polynomials in an ambient space that is given by a product of complex projective spaces. The multi-degree of the polynomials are encoded in a configuration matrix where in every column we have a different polynomial, and in every row we have a different ambient space factor. Just as an example, say polynomial P2 has degrees 2, 1, 1, means that polynomial P2 has degree 2 in the coordinate of the first P2 and then degree 1 in the coordinates of the other ones. Of course, to cut a threefold, I need to have that the dimension of ambient space minus number of equation is equal to 3. And there is also one extra equation enforcing the vanishing of a first-Chern class in order to have a Calabi-Yau. Famously, a list of 7,890 possibly distinct Calabi-Yau manifolds was constructed in this way. And the important thing is that this list is exhaustive. So what I mean to say is that you could try, if you want, to start with a different ambient space, a much bigger one, for example, much bigger number of equations. Whatever you do, you will find a Calabi-Yau that is already contained in this set of 7,890. So we want to look at this Calabi-Yaus, and we want to look if we can find small w naught within this set of Calabi-Yau manifolds. In particular, however, we want to focus on compactifying on the mirror of this Calabi-Yaus. Because remember, in the prepotential for a complex structure, the coefficient that appear are related to topological properties of the mirror of my compactification manifold. So I compactify on mirror CCs, and then I use topological information of the CCs to do my analysis. For simplicity, we also focus on a very not so ambitious, maybe case of just focusing on H11 equal to 2. We do this for two reasons. First, the scan is already reached at this level, and second, in this case, all Kähler cones will be simplicial, and so it will be easier to analyze. We have 36 geometries in total, and we want to scan over 3 among the 4 fluxes that I have. So remember, H11 equal to 2, so I have F1, F2, H1, H2. The fourth one is fixed by enforcing the orthogonality condition. That's a necessary condition for the small w naught. We set by end a range of minus 300, 300 for the flux. And also, importantly, we give results as a function of the D3 tadpole. Why do we do this? Well, we do this because we actually do not know what is a full classification of the orientifolds of the mirror CCs. A very good database of orientifold of CCs was done by Alexander Westphal, Jakob Moritz, and myself a couple of years ago, but not for mirror CCs. So what we do is essentially repeating the analysis for all the possible values of the induced D3 plane charge that a given orientifold on those manifolds could have. And we look for vacua that are possibly existing according to this constraint. After we find these candidates, we also check that the valley can be lifted. In particular, we have computed the Gopakumar-Vafa invariance. And as a final check, we check that what we find is actually in the physical reason, so small coupling for the axiodilaton and large complex structure. That is a consistency check. Otherwise, what we do doesn't make much sense. So let me propose the results. So this figure has to be read in the following way. The different colors are for the different values of the D3 brane tadpole, essentially. We find that, of course, increasing the tadpole, we have a larger number of possible vacua that we find. And so we find that it's essentially quite generic. Not all the Calabi-Yaus will give small w naught, but also it's not that just 1 or 2 will make it work. So I'm showing here the case for CCs that are K3 fibered, and this is the case for non-K3 fibered. We do find that somehow when we work with K3 fibered case, it's actually a bit easier to find small w naught. I don't understand well if there is a physical deep reason for this or not. For each one of these cases, we actually do the stabilization explicitly. So for just an example, we find the vacuum and we are actually explicit on what are the fluxes that we choose, what is the vector M that does the work. We check that is still weak coupling and that we are still in a sufficiently large complex structure. And we find the W naught from this particular case that is 10 to the minus 7. Just to say the record W naught that we find in this class is something like 10 to the minus 27. We provide a database as an attached ancillary file on archive, and we give all the details for this possible vacua that we find. So very good. That was essentially 3/4 of my talk. I would like now to change gears completely and discuss something else that we did. And this is not about small w0 anymore. It's related to the topology of the divisors that we have for complete intersection Calabi-Yaus. So in particular, it's important in order to generate a non-perturbative superpotential for the Kähler moduli to have some divisors of my compactification space that are rigid. Because in this case, wrapping a D7 brane or a E3 brane, then I can get that AE to the minus AT term in the superpotential that we were seeing before. So what does rigid mean? Rigid means that there are no normal bundle deformations for these divisors. In some sense, you can think of it as being like stuck in the Calabi-Yau. You cannot move it much around. Another way to say it is that the line bundle dual to the divisor is a unique section up to scaling. Or another way to say it is that H20 of the divisor should be vanishing. A necessary condition for having a non-trivial superpotential is having that the arithmetic genus of the divisor is equal to 1. So we are interested in looking for rigid divisor in the set of CCs, because say, for example, that it was possible to prove that there are no rigid divisors at all in this set of manifold, then it would be a bit harder, not impossible, but still a bit harder to do Kähler moduli stabilization. Okay. Another type of divisors we care about is aim-pole divisors. I will not go much in the definition of aim-pole for a question of timing. I would say just why we care about aim-pole divisor. So if a divisor is aim-pole and also rigid, a single E3 or D7 brane wrapped on this divisor can stabilize actually like all the axions of the Kähler moduli and the combination of the C4 axions. Essentially, we will have a superpotential term of this type where inside a single exponential, all the Kähler moduli enter. So it's very practical to do Kähler moduli stabilization if we can use aim-pole and rigid divisors. So there is a question of looking and seeing if we can find rigid divisors in the CCs. Of course, the set, the number of divisors is like infinite. It's like a lattice, but we want to focus on divisors that are very simple just to start. And so we look at coordinate divisors, which can be defined by setting to 0 one of the homogeneous coordinate of ambient space factors. Another way to say it, we care about these divisors that are pullbacks of the hyperplane classes of the ambient space. Now, the Hodge numbers of the divisor can be computed. This is the mathematical problem that is solved, yet for me personally quite hard. They can be computed by Cos-Joule spectral sequence, which in turn can be computed if we have knowledge of the line bundle valued cohomologies for the Calabi-Yau X that we care. Luckily, this computation with the Cos-Joule spectral sequence and so on was coded for us. And there is a program called ComCalg by Blumenhagen et al., which can do this computation, as well as other programs like pCICYs by Maddalena Larfors and collaborators. Anyways, all these programs start to be very, very inefficient as soon as you increase a bit H11. We are talking about days of computation to get just one Hodge number for a divisor. So it's slow. So we had an idea to circumvent the problem, and the idea is the following. The Euler characteristic and the arithmetic genus of the divisor can be written in terms of the odd numbers of that divisors. Okay, and then by some index theorem, as usual, quantities of this type can be related to integrals of like topological quantities, like triple intersection numbers, values of second germ form, stuff like that. What I want to say is that we know to compute well the right-hand side of this equation. So you should look at this equation, think here there is a number. So we have numbers here, and here we have what we want to find. However, it's like two equations for unknowns. So, well, it would be very nice if there were two equations for two unknowns, because then I could solve them. And in some sense they are, because we conjecture that for all favorable CCs, divisors of this type are connected and also simply connected. So the H00 is 1 and the H10 is 0. We check this with this concalc program up to H11 equal to 6. At some point, we believed we had a proof for this, but we ran into a small technical detail that made us feel unconfident to state in the paper as a proof. So we state it as a conjecture. Anyways, if we conjecture this, it's driven out to solve two equations for two unknowns, and you get to a structure of Hodge diamond of divisors of this type. Very good. Now I want to ask you a question. So we have a set of 7,820 manifolds, a set of 57,885 coordinate divisors. Think in your mind, how many different Hodge diamonds could we have? Like which order of magnitude? Think of it for a second. The answer is actually 11. So out of this big database of manifolds, we just have 11 different type of coordinate divisors that can appear. Most of them are K3s, and this is not a surprise. We know most of the CCs are K3 fibered. However, there are also other complex surfaces that can appear. The important thing here I would like to notice is H20. So H20 is never 0. So coordinate divisors are not rigid for CCs. Am I saying that you cannot do CCs, you cannot have CCs to do Kähler modular stabilization? No, I'm not. You could look at linear combination of divisors to wrap your D7 branes. You could look at non-rigid force cycles that can rigidify by work volume fluxes. However, I am saying that if you try to do Kähler modular stabilization with this class of manifolds in the most possible naive way, you run in some issue maybe. Let me conclude, because according to my watch, I have 2 minutes more. So let's summarize the result. We find an abundance of possible perturbatively fluxed vacua among the mirrors of the CCs. We actually do also complementary analysis in Kreuzer-Skarke, still at H11 equal to 2, and I didn't have time to talk about it, but you can find the paper on arXiv if you're interested. We are actively working on pushing it to higher H11 in both databases. And then we also classify topologies of coordinate divisors in the CCs, finding that none of them is rigid. Stuff done for the future, there is always a lot of stuff to be done. Would be very interesting for me to understand better the orientifold of mirror CCs in order to be more systematic about what really is the D3 brane charge on the O7 locus, and to be more specific about the tadpoles and even the existence itself of this candidate vacua that we find in this paper. It would be useful or nice to push this scan at higher H11. And also, I want to point out that there are some interesting construction and databases for Calabi-Yau manifolds that have been essentially completely unexplored from the model building point of view, like, for example, generalized CCs, which is something I would like to look more in the future. Thank you very much for the attention.
Thanks a lot, Federico. So are there any questions? If yes, please raise your hand. So while we wait, maybe let me ask one. Oh, there's already two. Okay, so I'll as a chair, I'll give the word to Fabian, please.
Hey, Federico.
Hello.
Thanks very much for the nice talk. I just wanted to briefly ask, is there the mirrors of CCs, are they toric hypersurfaces or are they also toric CCs? I mean, in general, I would expect they are toric CCs, right?
Yeah, so I would think so, but I'm not sure. For sure, they are not in the CC dataset, so it's not like Kreuzer-Skarke that all the mirrors are inside the dataset.
No, they can't be, yes.
They can't be inside the CC dataset. I would say that, at least naively, complete intersection in generic toric Fano ambient space would probably allow for them to be present, but I don't know for sure.
Can I make a comment? Or
Yeah, sure.
Sure.
By the paper, in the paper by Petrev and Borisov, they classified or they studied how to construct the mirror Calabi-Yau of a generic toric complete intersection. And given the CC is also a subclass of the toric complete intersection, you can follow that algorithm to construct the mirrors.
Yes, of course. The question was just whether so does the fact that, let's say, the CC needs, I don't know, an F partition with three hypersurfaces, is this preserved under the mirror map, or could it be that sort of a CC is mapped to a hypersurface in the dual?
Generically, I'd expect that the Neff partition, you should still take the non-trivial Neff partition. I'd be really surprised if some of the not very highly non-trivial CCs become a hyperplane in a toric hypersurface.
Yeah, me too. Thank you very much for the comment and for the answer.
Jakob.
Hey, Federico, thanks for the nice talk. I had a question regarding the rigidity of divisors in CCs. So the hyperplane classes are all non-rigid, but have you, so I'm not sure if this exists in CCs, but there are often effective divisor classes in the Calabi-Yau that cannot be obtained by pulling back, by just intersecting a divisor of the ambient variety to X.
I agree, yes.
So in toric, in toric hypersurfaces, it happens quite often that such divisors do exist and they are rigid. I'm not sure if they can exist in CCs, but have you looked at that?
And that's true in the CCs too.
Sorry, somebody else said something.
Sorry, it was me. I just happened to know the answer to that one. It is true that they do appear quite often, and they're quite often rigid. Yeah.
Okay.
Sorry, Federico.
It's okay.